here. Okay, thank you very much for coming to this talk and for Sherry to letting me present this work. Basically, it's what I'd like to, my message today would be basically to show what we've done related to this Gondwana, new Gondwana map that I will present to you, and what were basically the challenges and the advances we had during the project. The map is already, it's still not published, and I would like very much to get these people from the supercontinent IGCP to see how can we actually interact and what would be important for the IGCP648. That will be the outcomes from the IGCP648, which is the IGCP that I lead it about the Gondwana continent. Okay, so as Sherry told me, I am currently at the University of Bern doing some work on the shear zones with Marco Herberg. Okay, so this is the main product of our IGCP, and as I told you, it's still not published. And what I think would be a message for here, this group specialized in supercontinental growth and evolution through the Earth's history, it's basically to see what Gondwana can tell us about it. Yeah. So when we look at the Gondwana map, I would like to emphasize that this continent actually is a very anomalous one because it was held together for more than 350 million years. So it's actually, I consider it a supercontinent in this way. It's a large volume of mass that were together for more than 300 million years. And so we can still, even people say, oh, but this is a young continent, but I think it's the youngest and the most robust continental landmass that we can use to test a lot of questions that we have regarding the growth of the continents. So it's, I know a lot of people focus on the ancient paleocontinents, big ones, but this one actually is the one that has more evidence that we can test the hypothesis. For example, the recycling of detrital zircons and the juvenile terrains, what you can get preserved or not preserved. So I would like to show you today that this map can actually give us some ideas or at least some ways of going to testing this hypothesis. And we still have lots of doubts about Gondwana, even though we can reconstruct it from the actual, the modern oceans, we still have lots of questions. And some of them are regarding, especially this northwest part here, regarding the Pangaea connection, the Pangaea period of Gondwana, also the Panoche supercontinent in the Cambrian. So does it exist, or we actually have lots of questions regarding Gondwana, and that's what I wanted to show today. So the first part of the presentation is basically what I presented here in Bern 1 or 2 months ago, before the lockdown. And it's basically an introduction to the continent, which I think I will pass a little bit faster to get to the main point that I would like to stress here, which are point 4 and 5, about the reconstruction and about the outcomes. But still, we're going to start presenting what we call the supercontinent Gondwana. And it's all historically, it all started in this point here in India, where we got these amazing glossopteries, fossils, and all these Carboniferous Cretaceous sedimentary strata that were actually very similar to the ones they found in other continents, like Africa, Madagascar, South America. So that was where the Gondwana land concept started. Almost 200 years ago. And of course, in the last century, we have very nice publications in the time of Wagner and Vitual. And you can see we've been 100 years still discussing the same fit, for example, between the clearly obvious fit of South America and Africa, but we can see that it's still not so obvious. And of course, there are so many evidence for this supercontinent. And for example, the Zamfrau geosyncline or the Gondwanites, and we'll go all the way through this. So it's been for a long time known. And basically, I always describe the evolution of this continent as 3 periods. The first one would be the amalgamation, and it's all related to Rodinia, of course. So Rodinia was this supercontinent at breakup, so the fragments or the sons and daughters of Rodinia, as Professor Blay in Brazil says, Brito Neves, are actually going to converge in the end of the Neo-Proterozoic and make our Gondwana. So this, I believe, Meredith is also in this room today. I'm so happy to show this was one of the very nice work that we used also to discuss about the amalgamation of Gondwana. And we did a major compilation. This was part of the IGCP project that we leaded about how did amalgamate Gondwana. And we did a compilation of all the orogenic belts from Gondwana. And we got to these numbers here, which are the total time that it took to amalgamate Gondwana. So we believe it's going to be around 200 billion years. And the way the blocks were scrambled here at 780 and got to this point here, what we've known until today, they are pretty much close together, these cratons. So the way that they did it was not actually a simple way, like we used to say the East and West Gondwana collision is actually a little more complicated than that. So the 55 orogens that we compilated are here from 680 to 480 until the Ordovician time. And we have all the ages of the belts, and the blue would be the belts that are in the Eastern Gondwana blocks, and the red, the belts that are in the Western Gondwana blocks. And you can see that they are alternating here, the collisions and the amalgamation events. So it's actually, it was a convergent period of almost 200 million years that different blocks get closer together and finally collided. So with this compilation, we put in a simple histogram, so we can see here the age from 680 to 480, and we separate in 2 stages. The stage 1 will have fewer origins but wider origins, and they will be from 670 to 575, the end of the Ediacaran, with the period. And these ones are preserved basically in this red area that I call the phase 1 amalgamation. So basically you have the core of Gondwana in Africa, Northern and Central Africa. Of course, this is also the area that we have the less data, the Sahara region here, below the Congo Basin. So this is actually what we've done with the compilation that we have, but we have to point this out, yeah? And the second phase of amalgamation will be this one, where we have most of the belts, which are basically Ediacaran and Cambrian belts. And this will be like the end of the Suturine, so it's gonna be like a big ring around the main core of Gondwana. So this was something that we came out, and we did this because we needed this idea to put in the map the stages of amalgamation. This figure is already modified from what we published 2 years ago. So this would be Gondwana at 500 million years ago, with the cratons in pink. Of course, the light pink is the covered cratons. And the belts that I'm talking about, the 2-stage belts, would be first the orange and the dark green, which would be phase 1, basically here. And then you have the younger belt would be the lighter greens that I can see all around through the eastern blocks and going south here and to the Andean area. Yeah? And these are the blocks that drifted apart from Gondwana during its evolution that I will talk later. So we got the amalgamation period, which took 200 million years almost. And then we got the time, which is the 320 million years, which would be the period that this landmass was together. And we get this basically from the sedimentary intracartonic basins. This is an example that we did with the group from South Africa Brazilians and South Africans, correlating the major events that we can see in Brazilians and also the African basins. So we know that Gondwana was actually a continent as a landmass that gathered and registered the climate and life evolution during the Paleozoic and the Mesozoic Earth. So this would be the major landmass. Around it, I will apologize because some slides will not come as fast because the figures are quite, how do you say, they're quite heavy. Let me see if I already had this trouble when I was, yeah. So this is, it's now about the margin of Gondwana. Yeah, so this is another thing. We talk about the interior and what was happening during these 300 million years in the margins. We pretty much know that the northern margin was basically an extensional margin most of the time. And most of these blocks are now in Asia and Europe and even in North America. The southern margin, we had a lot of belts, and it was always a active and destructive margin with some riftings, but most of all, we had a lot of subductions, and they are still alive today in the Andes or in New Zealand. So this destructive margin is actually very complicated to reconstruct, that we will see later. And another thing that I would like to point out, the Pangaea blink that I say for Gondwana, when Pangaea merged here at this part, it's already started the breakup with the Central Atlantic Magmatic Large Igneous Province. And after this breakup here, Gondwana was never the same, and it started breaking and disrupting, that we will see later. So the breakup stage took 100 million years. And the last bridge, as we all know, is between Australia and Antarctica, which rifted after 85 million years. So it's related mostly to a lot of large igneous provinces that we will see. And the product is basically the rifted margins that we have today, the volcanic and non-volcanic rifted margins. And Colin Reeves has this very nice, I hope we can, there is in his website, he has these reconstructions that he does. There are movies, and he plots all the oceanic features that we can do to reconstruct that are quite good, the magnetics, the transform faults, and also the plumes, yeah, that were related to the breakup of Gondwana. I wish it was working. I also had this trouble before, but you can check on his website about this. So we can actually here, we can see the Camp, which is the oldest, and then the Beauvais, the Marion, the Reunion. Of course, this is in the actual time, but in his model, you can see the reconstruction to 200 million years ago. Okay, so about the project, I don't know if a lot of people know this project. It's been running for 8 years, and we are now working on the publication of the data. And it's called the Revision of the Geological Map of Gondwana. It was an IGCP for this period, and it's a geological map and the tectonic evolution of Gondwana. We had a lot of collaborations from a lot of institutions and scientists. Some of them are here right now with us. It was funded by the oil company in Brazil for these 9 years. Now there's no funding anymore. And the goal of the project is to make the Gondwana geological map, but actually, when we started, we already saw that this was a major challenge, because we cannot build a paleogeological map without understanding the process of geodynamics and the Gondwana evolution. So we had to do lots of modeling and exercise to produce this map. So it's not a collage like that. It's a little more complicated than this. And we had the 2 previous Gondwana map. This map was published from our friend and late Martin de Witt, that I will talk about him in the end of the presentation, that left us 1 month ago. And this map actually was a geological map, and pretty good for that time. Actually, is our reference map, and we try to improve this map. This map is in scale 1 to 10 million. The map that we produce is 1 to 5 million. It's a lot of more detail. This map is from Rafael Unruch. It's a more geodynamic map with interpretation of terrains, island arcs, and we wanted to make a more data-based map, not so interpreted. So our map is going to be is a map of geology, basically. So let's go to the products. Let's go to the discussion. So the first part of the project was to build up the database, which is quite complicated because of different backgrounds, different countries, and we have to put all this data integrate in the same legend and in the same geology, the same structures. So it took a while. Some places we got GIS for free, with good digital based and updated data. Some places we got old data. Like Africa, we had to get maps from each country, which was very complicated, and we had to draw the maps. I showed Madagascar, which has a very nice and young map, but we didn't have access to the GIS, so we had to draw the whole thing and do the vectorization and to do the digital stuff. Antarctica was also a big challenge for us. We had to work with papers, basically. So we took the figures from the papers and did the GeoRef, and we used the base map from '69, which was the geological map, the last geological map of Antarctica. And after we got all these polygons, we took all the data that we have from satellites, like the SRTM data, and we adjusted the polygons, interpreting how it would be the design of this geological unit and the structure to get a little more close to what we had. So this would be our basic data, our database. And of course, we had lots of polygons, but I just wanted to show you that we organized this. To organize this, we really need a very basic legend, a basic geology. That's what I'm going to show you. So the map is very simple in terms of geology. We have the oldest rocks are in these more hot colors. The youngest, the Phanerozoic rocks, are in these cold colors. And we have to change a little bit the IUGS colors from the geological time chart, and to see better the cratons from the Archean, Paleoproterozoic, and Mesoproterozoic, and then the Neoproterozoic, the Ediacaran in yellow, and then all the units from the Paleozoic. I have to check on the time that I don't see here. Anyway, the lithologies are very simple too: igneous, volcanosedimentary, metamorphic rocks, and sedimentary rocks. The igneous rocks, we could classify the geochemical of these rocks, if they are basic, ultra-basic. And the metamorphic rocks, we could add the grade, metamorphic grade. So we're going to give you an example how to read this map. So this is a southeast part of Australia and Antarctica together. You can already see the craton here, and then the Neoproterozoic belt, and then the younger belt, which is the accretionary Australian and Antarctica belt. And if you go do a zoom, you can see this is a craton, the Gawler craton. This would be a volcanic acid rock, a plutonic acid rock from the Mesoproterozoic, a Cambrian plutonic rock, and the Paleoproterozoic metamorphic rock, Archean metamorphic rock. And I would just like to point you out here, this polygon here, which is a Paleoproterozoic, just as this one, metamorphic, but the pattern is different. Why? Because this is reworked within the Neoproterozoic belt. We wanted to show how Gondwana amalgamated. So we wanted to separate very clear the cratons from the belts, even if the belts had this older reworked continental crust. So that would be this part here. So the metamorphic rocks, we can see also the age of the tectonic events that made this metamorphism. So like Southeast Brazil, it's clear here is the San Francisco Craton, which is in black, the Archean. But as you go to the coast, you see the cryogenian metamorphic origin, and then the Ediacaran Cambrian metamorphic origin. So you can actually see the growth of Gondwana, and then you're gonna be in Angola again. So now it's the main point I'd like to show you, which is the more controversial and was very complicated for us, which is reconstructing the Gondwana. So this is the second part of our methodology, reconstructing the Gondwana plate. And this hand, as I was told by Martin De Witt, this hand is from Jan Diel. And this is when they built up Gondwana map in 1988. And this was the way they built. So today we have more tools. And I don't think we can make much better than what they did because they were really great at that time. But we now can use the softwares and all this digital stuff here. But we know that the reconstruct Gondwana, it's a challenge. And it's been since Vitual. And now that we have this data, you can see that our map is much more detailed. It's a 1 to 5 million scale map. So we had a lot of challenges in this reconstruction. The first of them is the interplate deformation that we cannot ignore anymore. When we see Gondwana, we cannot say that this is a supercontinent, that it is an homogeneous lithosphere. It is certainly not, because it's a collage of several blocks, yeah? So there's not such thing as a homogeneous lithospheric plate, superplate. And why I say that? Because we know that the lithosphere is heterogeneous, the lithosphere behaves differently to deformation. So everything that occurs in the margins will affect here a lot. And this must be considered if you want to reconstruct a continent. So this is from Colin. I'm not sure this is gonna work, but this is the Cretaceous rift system of Africa. And to fit the margins of South America and Africa, you have to undo these rifting basins. And to do that, okay, you can see that. So the blocks are moving internally. So this is very important to make the reconstruction that we can take into account nowadays with all these mathematical models and all these software that we have. Let me see if it's not going. Okay, so how do we do this? So now we're going to talk about inheritance, which is very important to reconstruct. Lithospheric structures are very important, but I can want to point out here that even a weak lithosphere, which means that it's heated, hydrated, also exerts control, because it's not only the structures, but the petrology of the lithospheric mantle. So how does this mantle react to the plumes or whatever you have that will make it melt in the base? So it's very important what kind of terrain, not only the structure, but the composition of the lithospheric layers. So as we saw before, Gondwana was built like this, and we have the sutures. How does these sutures play a role in dividing the Gondwana into different blocks? So our map actually is not built up by South America, Africa, Antarctica. Our map is built up of these blocks. So these blocks, basically Antarctica, the core of Antarctica is one block like Australia, but the other blocks had to be broken, yeah? So I'm going to show you some results of the South American blocks that were, South America was actually not considered until recently as to be break into blocks. And we actually, this proposal that we did, it's from our one master student. She published it in Tectonophysics, this thing here that I will show you. So what she did, she studied, compiled, of course, the growth of South America with all these blocks from the Archean to the Neoproterozoic, and then she put the Phanerozoic units and the structures. And I will, of course, this is the Trans-Brasiliano lineament, which is a major shear zone from the Neoproterozoic, and we have Devonian reworking, we have a lot of cataclysite showing that it actually is a weaker lithospheric portion of our South America until today. So what Pamela came out with these blocks here, based on geology. And so, for example, we have this Northeast Brazil, that we have the structures that go all the way to Africa, the piercing points that I will talk sooner. And in these places, we had to cut the plates. So these terrains are actually separated, although they are called today South America. This is a dike swarm. This is a Cretaceous basin, and this is a Cretaceous dike swarm, which actually showed the interplate deformation. So Pamela matched the South American blocks with African blocks, and she did quite we think it's a good fit. And we had, of course, overlaps and gaps. Yeah, the problems are the gaps. So these overlaps are the continental ocean boundary overlaps, which I will talk soon. But the gaps, yeah, this could be related to stretching, microcontinents, but the gaps are a problem. In these gaps, we will see it's exactly where we have the Falklands Plateau, and I will talk about that too. So this is our final model for this map of this year. And this is the plate circuit that Colin Reeves likes to make, and we made it for our model. We fixed all the blocks in South Africa. These are the parameters, which are the angle of rotation and latitude and longitude of the blocks. So about the piercing points would be more a continental reference that we have. This paper from Martin was quite good on our discussion about matching South America and Africa. And so the piercing points are actually structures that are terrains that we can say that they are actually belong to different parts of these different continents today. So it would be this kind of structures, tectonic contacts, volcanic deposits, different similar terrains of evolution, and even zircon provenance patterns. Like, for example, again, in Southeast Australia, we have this limit, the surface limit between the Craton and the Neoproterozoic belt that might continue to Antarctica. So this would be a good continental piercing point. We can have also the rifts, the Cretaceous rifts between Antarctica and India that we also used as piercing points, or the more complex match between Sri Lanka, and we know already that this is the one we prefer, but still we had other proposals based on structural orientation of foliation. But we did a lot of research, and we have a master's students finishing this right now, and we know a lot of other people are working with this data, these terrains. So if we understand the barcode of each terrain, so we make a big table like the one Igor did, and some of you probably know Igor. He was in the field trip in Madagascar last year for the IGCP. So you can put all the data here. Of course, I'm not gonna, and then you can match the similar data like neodymium signature, the detrital zircons, the age of the magmatism, and make these maps like the age of the orogenic belts, the age of the igneous units, and the neodymium model age and the structures. So after all this compilation, Igor came with this fit for Madagascar, Sri Lanka, and India. And what I would like to point out here is that you see, of course, the overlapping of the margin. So until now, I was just stressing out here the continental deformation, the continental piercing points. Now I'm going to talk a little bit about the margins. How I'm doing with time, Sherry. Can you just show with your hands how much? It's okay? I have 10 minutes? Good. Thank you. And okay, so let's go to the continental margins. And they're quite complex. We continental geologists usually forget about the oceanic plate and the continental margins. And after this work with oil geologists, we learned a lot about it. And we learned that they're much more less known than we thought there is. And for example, if you see the continental margin of Brazil, this is the coastline, this is a bathymetric map. This is the COB inferred, which is the continental boundary, and this would be the OCT transition zone. So it's a lot of guessing because the margins are quite different. This is a hyper-extended margin, and this is less extended. So this makes a lot of difference when you want to reconstruct. So here, what are our problems? Where are the COB? You must have not good seismic data to know that, or even the drill holes, which will be better. The imprecise magnetic anomalies, this is very important for the South Atlantic, for example, because of the quiet zone in the Cretaceous, that we have 40 million years without reverse of the magnetic pole. So we have a lot of guessing here. This is the Rio Grande rise, which I will talk very soon about it. But we have some certain things like this is the salt that deposited in our rift basin before the breakup. So the salt was deposited in continental crust. So we can have this nice evidence. So these are our Gondwana map. We have the COB line. So this is the COB line of Africa, the actual, and this is from South America. Again, this huge overlap. But there is a lot of things going on in the margin here that I will show soon. So talking about the margins, they have exhumed mantle, exhumed lower crust. You have the stretching of the crust. And of course, we have the pre-breakup offsets. Before you break up the continent, before you have the first continent, oceanic crust, you can have a lot of offsets of the terrains. So when we work with piercing points, we have to be careful because you must have some transtensional structures that might already offset the structure before the breakup. So you have a bad match. About the margins, we have the microcontinents. So if we look at the bathymetry of the actual oceanic plate, it's very diverse. So I'm going to start talking about this part here. This is the Rio Grande rise. It's a major volcanic structure or province that we have in the South Atlantic. It's in the coast of Brazil. It's 1,000 kilometers offshore. And this Rio Grande rise was actually known as to be a volcanic, like a big volcanic edifice. But actually, we know that the crust here is 30 kilometers thick, which is quite anomalous for an oceanic plate. So if you go zoom into this, you have the Rio Grande rise here. And there are these very interesting structures like the Vima channel, like the Cruzeiro do Sul lineament. And what we know about geophysics here is that we have a very good magnetic response in this part in a very thick crust. So we think this might be actually magmatic, volcanic, 80 million years old rocks. But to the west, we have a very low magnetic signal and still a thick crust. In addition to that, we have these continental rocks that were sampled in this region from the bottom of the ocean. And we can have a very nice signature of the Brasiliano belts and the Angola belts in the other side that shows that these rocks probably came from Angola or southeastern Brazil. So if you look here, 90 million years ago, that would be with the reconstruction, we know we can see a major volcanic structure in the ocean, like Iceland today, and then it will evolve, and I will show here the model from Graça. So she interpreted several ridge jumps. And because this is a very anomalous crust, we think that part of this, not a lot, maybe less than 10%, would be continental crust. So this would be a microcontinent. Of course, we all know about the Mauritia. And yeah, in this case, we don't, it's not emerged, the continental crust, but we have the zircons that might show that we can have, like this model from Igor, we can have in the feet of Sri Lanka, India, we can have Mauritius here, Seychelles, which is emerged, of course, and all these other blocks that might be in between the major Gondwana blocks that we might consider. And then we go to New Zealand, which is very tricky, complicated. 10% of New Zealand is emerged. And we know it's considered the 80th continent on Earth. And you can go very well to the 30 million years ago, you can reconstruct New Zealand. But the problem is to go back to Gondwana margin. And then we have very few data. Actually, we have a lot of data, but very few data to kinematics to reconstruct it. So what we use the traditional geology. We use, for example, the belt here, the Carboniferous igneous belt, the Cretaceous core complex that we have here to reconstruct New Zealand into the Gondwana margin. And then in the end, we got this. And I will talk now about rebuilding the Gondwana margins. And then we go from New Zealand to these blocks here. And I'm glad that Ian is here watching us, because basically what we did, we used the same reconstructions that Ian did. We still don't have good oceanic data from the oceanic crust to make this reconstruction. So we need the geology of this inland data. The peninsula, it's quite well tighted here to the southern Patagonia. And this part here, we basically use the Ian reconstruction. So if we put all these igneous rocks from the Ross origin in the Cambrian to the, I'm looking at Ross right now, to the Devonian here, igneous rocks, and the Permian rocks, we can see the migration of the active Gondwana margin. So this is one way that we can rebuild and reconstruct these blocks here. And then we got in the end to the Malvinas Falkland issues, which was not very easy for us. We had to make a workshop last year only about it. And yeah, you have the Falklands Malvinas Plateau, and we are following the proposal from Victor Ramos. So here he shows that we have the Vitual first idea to put in the South Atlantic, which of course we know it doesn't work. We have the AD proposal that rotates the Falklands 180 to this position. In this, you can match the versions of the Permian belt, which the folds in the Malvinas are version to the south, and in the Cape Fold are version to the north, and also in here in Argentina. So you had to rotate the Falklands. We had a lot of problem doing that. So this would be the belt that we were talking about. The Ellsworth Mountains fit very nicely, but we had to put the Falklands here. And it's impossible for us. We're using the oceanic data. So this is more or less what we would like to stress. I suggest you invite Victor Ramos for giving a talk here. So this would be the position. People rotate a little less, make like an orocline here, but still it doesn't, you don't have oceanic data on that. What we know that the Falklands are attached to Patagonia. There is not any structure here that we can see from seismic, from mag, from graph data that shows that there is a collision between this and this, that this would be attached to Eastern Africa. So this is a very hard talk. And then you have the major plateau and the Ewing Bank, where you have these continental rocks from this part here. This is the model from Victor Ramos. He put Patagonia in the early Paleozoic in Antarctica. So it was rifted from Antarctica and collided in the Permian with the southern part of Africa and South America. So that would be the idea. So in order to make this, put on Falklands here, you really need to disrupt South America in this fault. And there is not such evidence in the continental, like the evidence I talked before, cataclysmites, there is not such evidence for this gastric displacement here. So it's very complicated to sustain this. On the other hand, between the Falklands and the Mauricio Bank, you have, of course, a very thin continental crust or maybe oceanic crust. So this paper shows that you might have oceanic layer here, but still you have a lot of continental crust within the Falklands Plateau. And this might be part of the Patagonia block. So this is what we came in the end of this. We have a major Patagonia block, including the Maurice, the Falklands, and all these blocks in the southern part of the peninsula here. Okay, about the margins in the north, I think now I'm getting, yeah, the margins in the north, we didn't evolve a lot. Of course, our map is from the Jurassic, so it's 180 million years. So this part, most of the things are already gone. Only the Afghanistan block we kept in our map. So most of the things were already in Europe. And the advanced, I think most I already showed. We filled some gaps. So we have like drill holes from a lot of places in the continental margins that we could put in the map, like this one in southern Brazil. And we have like, we can continue some belts, like this belt here, the Permian belt. We have seismic data that we can follow the deformation from the Permian. And Antarctica, what we did, we added bed map data, and we interpreted some rifting and some magnetic anomalies in Antarctica. So we will not have a blank Antarctica, and we can actually follow the blocks within Antarctica. So that was basically what we could do with Antarctica. And some overlaps, very few. These overlaps in Mozambique is the one that we have considered that part of this would be oceanic crust that we have now in the continent. And of course, we have overlaps in the Himalaya part, and this is what's going to be too hard for us to. So what we do in the map, we show the drills, we show basically the plateaus, and people can do this with the data later. We can do more science. So this is a Jurassic Gondwana. This is the Gondwana without the Cenozoic, without the Cretaceous, and that's what was our final decision. The Gondwana will be reconstructed for Jurassic, but the units will be until today. Otherwise, the map would be very blank. Yeah. So the outcomes, this is the evolution of the map. And this will be published this year, like this. It's a very big map. It's like the geological map of Asia. And of course, we will try to publish also the per continents, the actual continental maps, like the Antarctica, like the South America, which I think it's very important. I'd like to stress out that I don't see in these talks many data from South America. And I think maybe you can use a lot of, this is very updated. Our data is all updated with papers, like the last year papers. So you can use this data, which are quite, especially from South America and Africa, which I think it's most problematic in the giving data to the community. Anyway, these are this is, I'd like to show Cherie here in Madagascar to show we did some field work, and these are the places that we've been to discuss these piercing points during these years. This is where the Gondwana map started, this project in 2008 in China, thanks to most of these people. And we had lots of meetings abroad and a lot of people collaborating, and I thank very much these people. And this is the last meeting we had. We had Vitor Ramos from Argentina and David McCarthy from the British Geological Survey. It was quite important because we really needed to make Falklands in the map that they agree at least a little bit. So it was quite an important meeting. Okay, we had some museums and we have an exhibition in Rio de Janeiro also. This is the team. I really would like to show the team. I know I'm a little out of the time, I'm sorry. And this team is in Rio. Most of them are already unemployed because the project ended. But I would like to talk a little bit about Martin that died 1 month ago. Martin was in the first year of the project with us. And he was the person that actually told me, oh, it's possible to do it, because this was the really only person that I actually knew that could tell me this. And we are very sorry that he left us, and we plan to launch the map in his honor, basically. We were in contact with him and his team. And yeah, this is basically, I did a talk in Brazil to make in honor for him. And he'll be missed, surely missed. His production, I don't need to tell to everybody here, everybody knows. And especially the data that he did about developing people, developing countries. And this was quite good that he could apply science to people, which is quite a very important project that he did. And of course, the Gondwana map from 1988, these pictures he gave me when he was in Rio. And you can see a lot of guys, not many women actually. And you can see Jan here. And these guys were actually the ones that built the first Gondwana map. And I also, Martin did the digital base in the end, and in the end of the 80s, where we didn't have digital, good digital database, so he did it, and that is when he was in Rio. I'd like also to show you that we had a Gondwana meeting every 3 years, and we were supposed to have one this year, and we didn't have time to organize, and also this Corona crisis. So I'm proposing, actually I was proposing this before Martin passed away, to make in Africa, especially in Namibia, where I talked already to the survey, and I would like the support from the IGCP to organize this meeting. Of course, it will depend on the crisis, to organize the 70th Gondwana meeting, which is a very traditional and very important meeting that we've been having since a long time ago. The last one was in Thailand in 2017. So I would like your support on this. Yes, I'd like to thank you all, and I'm sorry for surpassing the timeline. Yeah.